So what I'm going to do is discuss the evidence that we have for an underdensity in the local neighborhood out to 200 megaparsec, which ultimately may affect the SHUs, the Adam-Rees distance scale estimate of H0 by something like 2 or 3%. And then I'm going to look at other potentially neglected SHUs, you know, the supernova cosmology for H0 and equation of state, that group, Adam-Rees's group. Look at some other potentially neglected errors. For instance, looking at Gaia versus HST parallaxes. Is there a variable reddening law even in the galaxies that they haven't accounted for in their errors? And also a Cepheid period luminosity incompleteness bias that we might see. Then go on to say what the effect of that is on the H0 tension. But then I'll try to explain, or at least look for what possible new physics there might be in the new tension that arises between the local hole and lambda CDM, even if you think you've then solved the H0 tension. So we'll go back to 2014, a paper from a PhD student, Joe Whitburn, and myself, Whitburn and Shanks, 2014. There where you look at NK and NZ to something like K of 12.5. Yeah, why not? Yeah, that works. Yeah. We're going to look at their NK and NZ, and we're going to look at it in these areas of the sky covered by the 6DF Galaxy Redshift survey in the southern hemisphere, these two areas here, and the SDSS survey, Redshift survey in the north. So these are 3,000 square degree areas, and we'll term them with this color scheme for the two, orange for this SGP area, red for this NGC area in the south, again covered by 6DF Galaxy Redshift survey, and SDSS goes to this green NGC area. So first thing you look at is the number magnitude counts, number versus K magnitude. So that is this column here. These are number on the y-axis, K on the x-axis. Then you convert, so you see that you start to see an underdensity, particularly in the SGC area, where the counts are lower than the homogeneous model given by the red line. You then convert that underdensity into a density contrast, delta rho over rho. And then you see that in each of these three areas, there is a underdensity, particularly in the South Galactic cap area, but also in the northern area, and also in the red 60F NGC area. So what you see is something like a 20-odd% underdensity overall. Much more clearly, you then plot the number redshift distributions from the 60F and the SDS surveys down to K of 11.5. And again, in these three areas, you see something of an underdensity here, a bigger underdensity in this SGC area, and then still something of an underdensity here. Divide the red line, which is our homogeneous model, by the data, so you get 1 if the density is average in the place in the redshift range that you're looking at. So you see a slight underdensity again in the 60F NGC. You see a much bigger underdensity again in the 60F SGC area in the South Galactic cap, and then again quite a big underdensity in the north and Galactic cap with the SDSS data. And overall median underdensity over something like 9,000 square degrees, these 3 times 3,000 square degrees, is 23%. So this is just zooming in on that area where you get the biggest effect, and you see that out to 150 h to the minus 1 megaparsec, something like 200 megaparsecs with little h of 0.7. You're seeing this under density here, which we're calling the local hull. So you then can look at X-ray clusters like Hans Bohringer and others did at 2015 and 2019. This is again comparing the SGC area. So the red points are the points I just showed from us in the hands of Bohringer et al. They go out to much higher redshifts than we did. We only went out to 0.1. And you see the blue points here are their X-ray clusters from the reflex ROSAT X-ray sample. And you see that broadly speaking, in the overlap area, there's very good agreement between their cluster data and our, their cluster data and our X-ray cluster data and our galaxy redshift data. So it gives you the idea that this is an observation which is reproducible no matter what selection you're using. But then there's the problem that other people have not seen this under density that we claim 20% out to 150 h to the minus 1 megaparsec. And one of the biggest discrepancies is with these authors, Jash and Laveau. And Laveau and Hudson also worked earlier, and we'll come to their work in a minute. And they claim to see no local hull using much the same data as we did to claim the local hull in terms of the redshifts and the two mass magnitudes. But if you notice, there is, again, in this southern area where the effects are bigger, you see this big dip here corresponding to this dip here corresponding to that dip there, and so on. And so you're clearly, the same data is shining through, it's just that their normalization seems to be different from ours, and that's where they're missing the local hole that we are seeing. Because when you compare the parameters, you compare K corrections and even evolutionary models for how the galaxies are evolving throughout this redshift 0.1, 0.2, even though there's low redshift, there could be evolution. But there are K corrections and evolutionary parameters very similar to ours, no difference there. But the main difference is in the luminosity function, where effectively Laveau and Hudson, whose luminosity function is being used by Yash and Laveau, they get something like, in terms of phi star, a 1.7 times lower normalization for their luminosity function. And that's, anyway, so the idea is that they use just the local area, local volume to estimate their luminosity function. And of course, therefore, by definition, it's going to fit perfectly. We historically, doing fainter galaxy number counts, have always normalized around about this redshift 0.05, 0.1 area in the galaxy luminosity function. And so you see that here. This is the black line is Laveau and Hudson. So they are fitting very well in this number count region down to 11 or 12 magnitudes. And everything's going swimmingly. But then their model totally underpredicts what's happening down to K of about 15, which is just G of about 17. So it's only redshift 0.1. So again, you don't have much controversy in the K band about evolution. Evolution rates are going to be small at these low redshifts, particularly in K. And so our argument is that our red line here, which shows an underdensity down in this area, but fits much better up here, is the correct normalization for the luminosity function locally. And therefore, that is our argument that this is corresponding, it's under density here is corresponding relative to the red line, that's our local hull. And it's possibly because Laveau and Hudson and Yash and Laveau have used this local determination luminosity function that they've effectively normalized out any underdensity that they've got, that they could have seen. So that was an argument we put, I think it ended up Shanks 2019 paper, along with various other issues that we had noticed about the Gaia data. I'll come to that in a minute, in terms of in the shoes, Adam Rees' hands. And there were various Rees rebuttals. Now, it was annoying this because I'd consulted with Adam for about 4 weeks before we put our paper on archive. And then one day afterwards, when we went into publication, at least on archive, there was a rebuttal paper came out. So it advises me not to consult the authors of papers that you're going to criticize too far in advance in future occasions. But anyway, so what he said was that, so we'd used our underdensity and then used simple linear theory to calculate what a 20% underdensity locally would mean for the expansion rate. And what it means is you get something like a 2 or 3% increase in the expansion rate because there's less mass below 150 megaparsecs to hold the expansion back. And so you get a too high Hubble constant like 73 rather than 70 or 71 if you take this local hole into account. But Adam pointed out that we had only done 3 times 3,000 square degrees, 9,000 square degrees, and the whole sky is 35,000 square degrees, say. And so it was unfair that what we'd done was, to base our dynamical estimate of how much extra expansion you got from this local underdensity as if it were applied to the whole sky. Now, at that point, I should have realized earlier the 2MRS, the 2-mass redshift survey, it goes to K of 11.5. I never realized how close to the galactic plane it claims to be complete, and it claims to be complete to something like plus or minus 5 degrees in galactic latitude. So therefore, with a student, Jonathan Wong, we went on to exploit the incompleteness of 2MRS to explore the full sky, basically 35,000, everything except the galactic plane. So just looking across the sky now at number counts to K of 11.5, this is the density. Oops, this is the density. This will be the density, hopefully, up here. You see blue means low density. So what you're seeing is more blue and green everywhere. You never see it going up beyond 0.1. Everything is reasonably in the low density area. Of course, the galactic plane area is here where you can't do anything, but that's quite a small area. So this is 90% of the sky. And you're seeing under density, not just in the 9,000 square degrees that we saw in the Whitburn and Shanks 2014 stuff, but you're seeing the same result replicated over the whole sky. So we rebutted Rees's rebuttal with that information, also showing this result. This is now the NZ again over the whole 90% area. This is the Laveau and Hudson. So if you believe the Laveau, Hudson, and Yash luminosity function, the local area is actually overdense, right? You've got more galaxies here than predicted. Believe our luminosity function, and which fits the fainter data better, then you've got an underdensity called the local hole, and this is it now in sort of density contrast, underdensity all the way again in this 90% all sky area out to, again, something like 150 h⁻1 megaparsec. And again, you can check, here we've checked with the gamma area down to K of 15 now, because they've got good counts over 210 square degrees. And the blue line is our model based on our luminosity function, fitting nicely out in this fainter, higher redshift region between 0.1 and 0.2, whereas the Laveau and Hudson one again is low, and the same story is told with number counts here. Laveau and Hudson doing well down here where they've normalized locally, but up here doing much worse, underestimating the actual count. So the summary for that is we would conclude that the local hole the Laveau-Hudson model normalization only works at K of less than 11.5, and that why they missed the local hole was that they may have normalized it out in their phi star for the luminosity function. A 20-odd% local hole under density reduces Hsu's H naught by 2.6%, as we said in the 2018-2019 paper. And now I'm going on to briefly mention other evidence of potential Hsu's error budget issues, but really the local hole is the only one I can point to say that is an effect that's going to change their H naught. The other ones are more speculative. So I admit that right at this point. So the first one is, in that 2019 paper, when the Gaia data had come out, we had complained, Reese in a press release at least claimed that Gaia parallaxes had confirmed his Milky Way Cepheid distance scale, which mainly came from HST parallax observations. And when we plotted their data versus ours in terms of distance modulus, if you use all 15 stars that HST had measured parallaxes for, you got a 0.181 too small distance modulus, or too small distance with respect to the Gaia measurements. And if you did 10 stars with which are the fainter ones, which you might rely on the parallaxes from Gaia more, just using those 10, you're up to 0.285 offset in distance modulus, which means that the previous HST parallaxes were 14% too small. Sorry, the previous HST parallax distances were 14% too small. And so, and this over here is why you might only believe you can believe very well, I'm not going to get time to go into this, but you might believe very well the Gaia parallaxes to G of 5, maybe not beyond there, not brighter than there. And I say, if you just take them down to G of 5, no brighter than that, you get a bigger 14% error in the implied for the previous HST distances. You then wonder how on earth did Adam then get the same H naught? And that's because he's not just using Milky Way Cepheids, he's got two other calibrating anchors, and somehow the offset in this one, the Milky Way Cepheid anchor, which is by far the most accurate, it must have been offset by different results on NGC 4258, the Mesa galaxy where it has Cepheids, and the LMC where he has eclipsing binary. Briefly, another thing he doesn't seem to worry too much about is, does the reddening law in the galaxy vary? This is open cluster data. I'll just point you at one of these, this one here, which is NGC 7790. This one's one of the furthest open clusters that we're discussing here at 3 kiloparsecs. And this one has always been the one where this reddening law in U minus B and B minus B fitted least. And you see now, if you draw the ratio of EU minus B, E B minus B against distance, you find this correlation, which said it might be a different extinction law at 3 kiloparsecs away from us than nearby. And of course, Walter Bader was asked by a reporter, if you had your life to live over, would you be an astronomer again? And the answer was, only if the ratio of selected to total absorption, i.e. that R value, is everywhere the same. So even if you haven't got a feel for what that does for the distance scale, it tells you how important this issue is. Won't go into that. That's Cepheid incompleteness bias. But some of these Cepheids at the more distant end have very sparse period luminosity relations from the Hsu's data, and that can make quite an offset, at least at the very most distant end of Adam's Cepheid scale. So the bottom line here is that applying the local hole correction, that's the only one I'm going to apply, takes you down from H0 to 73 with Adam, down to 71. So that's takes you from a 4.7 sigma H0 tension with Planck just down to 3.0 sigma. And if you applied any of these others, then you would get an even better agreement between Planck and H0. The problem is, apart from the chairperson approaching me now with a violent look in his eyes, is that you've solved the H0 tension at this point with a local hole, but the local hole itself extending out to 150 megaparsecs with roughly 20% under density, that turns out to be a 4 sigma tension with lambda CDM, right? You don't expect that sort of under density, 4 sigma in lambda CDM. So the talk could peter out here and we would all leave unsatisfied. But I would like to just suggest where there might be a possible new physics. If you got tired of looking for new physics with the H0 tension, you might get something more out of looking for new physics with a local hole tension. So I've just got 2 more slides, I think. So I'm writing down here other large-scale structured anomalies that everybody might like to think about. The 3 I'm going to look at very quickly is the CMB axis of evil, this one, the CMB cold spot, and another one, a periodicity that appears in the South Galactic cat that used to be reported by these authors that I was skeptical about, but I was less skeptical when we started to see the same thing in much bigger surveys ourselves. So in the way I would say the CMB axis of evil, this is the fact that this area here in the CMB and this area here on the side of this, 2 sides of this line look kind of similar. And De Oliveira Costa in 2004, based on WMAP data, tried to suggest this could be a signature of a complicated, non-simple university torus type topology, because if you're looking around the universe like the ant on the donut, you come back to the same place again, and that these 2 areas, then this one and this one, might look the same because they are the same, and you've seen around the universe back to where you started, and you've seen 2 sets of CMBs that are essentially the same offset to each other, and that's a signature of a non-simply connected topology. This is the second to last, the next one's a summary. So in fact, what we were doing when Mackenzie as a student, PhD student this time, was looking at the local hole area. That is actually this area down here, to check if there was a void of galaxies in front of the local hole, to check if that was an explanation through integrated Sykes-Wolf effect or some other effect that could explain the local hole. But by far the most interesting result we got was in this area here, which is the cold spot area where we had about 7,000 galaxies, and this black histogram is the NZ from that area. Something like 600 megaparsecs away was our control field, and both seem to give a kind of similar distribution, which is what Broadhurst, Ellis, Koo, and Zali claimed, and I was skeptical about in 1990, but this is a much bigger area and a much better redshift survey. And also between the 2 areas, you see the 2DF galaxy redshift survey not going as deep, but they also seem to reproduce the same thing. So this is a type of new physics you might want to check if, so what you're asking is there evidence for non-simply connected tomology? Okay. Yeah, and could a small universe make the local hole statistically more compatible with lambda CDM? And that's a summary, and I'll leave it at that. I'm sorry for going over time. Thank you very much.